So a couple of the other things that we know about the zeros of polynomials that we know for sure, even if we don't have any other information, is that for one, if a polynomial is of degree n, then it will have n roots, where that can include repeated values. So if we have, say, a 0 of multiplicity n for a degree n polynomial, that still counts as n of them. It's just the same thing many times. And then we also have that if the degree of a polynomial is at least 1, then we have at least one complex root, where that's not necessarily complex valued in particular, because remember, the real numbers are a subset of the complex numbers. So this is what's called the fundamental theorem of algebra, and it was actually the result that Gauss built his doctoral thesis around, interestingly enough. Fun fact there. And then finally, we have that if a plus bi is a root, then a minus bi is as well. That is, if we have one complex number or imaginary number for that matter, its conjugate has to be a root as well. And next, we're just going to get a quick example here, again, getting some things with roots. So for this, we want to solve x to the fourth plus x cubed minus 5x squared plus 5x minus 6 equals 0. That is, we need the roots of f of x equals x squared, x to the fourth, plus x cubed minus 5x squared plus x minus 6. And from the rational root theorem, that means we need the positive and negative factors of 6. So those are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Which means we might think to ourselves, oh man, we get to do synthetic division 8 times, don't we? No. Well, I mean, we can, but no, don't do that. Your time is more valuable than this. What you should do is plug in -6, -2, -1, 1, 3, and 6, and see that none of those values evaluate to 0. Check that you have any of them as potential factors first. And because 4 of them don't, just don't worry about them at all, and instead focus on the synthetic division for the 2 cases where it does, which, just to be sure, I am going to write out this time so we can actually see it. So, in both cases, we're going to have something in terms of that polynomial, which means 1, 1, -5, 1, and -6 as our coefficients, where in the first case, I'm dividing this by x plus 3. So, we pull down the 1, 1 times -3 is -3, that becomes -2, pull that up to get 6, that comes with the 5 to get 1, pull that in to get -3, -3 plus 1 is -2, and we get another 6 which dies and leaves us what we want. That if we take this here, what we have is one potential factorization, f is equal to x plus 3 multiplied by x cubed minus 2x squared plus x minus 2. And I'm low on space here, so I'm going to try and make this fit as best I can, but it's a little bit tight. Then in our other case, we have the same sort of setup on that first row, 1, 1, -5, 1, and -6. And here we're dividing it by x minus 2, so I'm going to put a 2 out there, pull down the 1. 1 times 2 is 2, pull down the 1, get 3. 2 times 3 is 6, pull down the -5, get 1. Times 2 is 2, pull down the 1, gets 3. 2 times 3 is 6, pull down the 6, gets 0. So our other potential factorization will be in terms of x minus 2 multiplied by x cubed plus 3x squared plus x plus 3. And you might look at yourself here and you might say, self, this looks like 2 perfectly good factorizations. How are we supposed to solve this? And I'll say to you, don't worry, self, because both of these actually themselves factor in to get the other one. And I'll focus on this piece here, but you can do the same thing with that one just as well, where what we can recognize is that with our x minus 2 here, we can actually factor this guy by grouping. That right here, we can pull out an x squared, and we'll have x squared times x plus 3. And then over here, I'm going to pull out a 1, just to make it clear what I'm doing. times x plus 3, and then we regroup as x minus 2 times x plus 3 times x squared plus 1. So, what we have as our roots there, if we're setting that equal to 0, would end up being 2, negative 3, and plus or minus I. Because you subtract 1, take the square root, you would get things involving I. And how you want to handle this can go in either direction, but we could have also done some work here using the factor theorem if we had preferred to clean these up a little bit. Like I've said before, there's rarely just one way to handle a problem of algebra. And if you like using this method, use this method. If you'd rather factor by grouping for that one because you see it easier, do that one. They're the same. They're just written differently. It's all a matter of how you want to handle that multiplication, how you want to handle that splitting. As long as you get to the right place, I'm okay with that. I don't need to force you to learn something in a specific way. I certainly don't need you to do 8 synthetic divisions. If you want to be a little bit more efficient, be more efficient. That's what I prefer. Get better things to do with your time. Anyway, that's another thing that we can handle here, another way we can go about finding our potential roots, our potential zeros. So next, let's talk about something to tie a bit of these things together with what's called the linear factorization theorem.